Okay, before we get started on Fiji and learning how to extract quantitative numbers, let's go through a brief introduction into image quantification. And we'll start off with something called intensity and thresholds. Now, if you attended the Fiji for Beginners workshop, you might remember me talking about intensity graphs and intensity ranges. So our image is made up of lots of different pixels, and each pixel has a different intensity value. And that's shown here on this intensity graph. So we have very low intensity pixels here. This is all the black background within the image, scaling up to the really high intensity pixels, so these more white pixels here. And this scale can be over different ranges, so 8-bit up to 255 grayscale values, 12 to 40,095, and 16-bit up to 65,000 grayscale values. We can make use of these different intensity values to basically thresholds to identify structures within our image based on their intensities. So in this case, we've got a little red box here. So we're highlighting anything that sits within this intensity value here in red on the image on the right. Now this is what we call an inclusive threshold, which identifies only the brightest pixels. If we go to what we call an exclusive threshold, we're looking at the dim pixels here, so only the ones within this red box, and that identifies the background in this image. Next thing we'll discuss is binary segmentation. So in this case, we're going to use a threshold initially to identify the regions we want to analyze, and then we're going to convert that to a 1-bit image. So here we've got our fluorescence image on the left-hand side and our binary image on the right-hand side. So the background that we haven't highlighted has intensity of 0, and the area that we have highlighted has the maximum intensity, so 255 in this example. And this is used to create masks for performing analysis, and we'll do this as part of the workshop today. So this is us saying only analyze the cells in white and don't quantify anything in the background. We'll play around with this a little bit as well. This is binary options. So we have the ability to modify these binary masks that we've created by doing things like dilating, which adds pixels onto the edges of objects. And for example, erode, which removes pixels from the edges of the objects. And there's examples of the dilate here. You make the structures go slightly larger, and erode here to make the structures slightly smaller. There are also options called open and close. Open, as shown here, is an erosion followed by dilation, and that has the effect of smoothing objects and removing isolated pixels, as you can see in this example here. A close is a dilation followed by an erosion, and that has the effect of smoothing objects and filling holes, as we can see in that example here. We can also combine the binary mask that we created with grayscale images to generate object-specific masks. So we can actually separate these masks out on a kind of per cell basis. And again, we have a cell segmentation activity later on that would be doing this. One of the other functions we can do is something called image arithmetic. This is using either mathematical functions or something called Boolean logic performed between two images. And it's very useful for combining masks, removing objects, or highlighting different objects. And we'll give a few examples of how that works over the next few slides. So in all these examples, I have two images with these mathematical symbols in them. Slide 1 has all 4, and slide 2 only has the 2 symbols at the top there. In this case, the image arithmetic we're going to do is we're going to add. So we're going to go pixel by pixel. So we're going to take this pixel intensity and add it to this pixel intensity and move across, right? So if we add, the result is that these top 2 get brighter. So we've doubled the intensity basically. and these bottom two have the same intensity as were found in slide 1 because there's 0 intensity in slide 2. If we subtract, then what we get is these intensities are the same, so it becomes 0, and then the intensity down here minus 0 gives you the same intensity as before, right? If we multiply, then again we're multiplying this times this, which gives us a very big value, and now you can see our scale has actually gone from 8 bits up to 32 bits, so we can actually incorporate these intensity values. These values down here have been multiplied by 0, so they are 0. And divide gives us a slightly interesting result. So the top values here are divided, so that actually gives us an intensity value of 1. We just can't see the intensity there because we're on a 32-bit scale, but there is an intensity value of 1 for this plus and minus symbols here. In this case, we're dividing these values by 0, which in Fiji world gives you infinity, so this is the 32-bit maximum scale. In terms of the logical, Boolean logic, we have logical ANDs, so objects which can be found in both images. So again, if we've got these, it's only the plus and minus objects which are found in both images. We have a logical OR, so it's in one object or the other, in one image or the other image, in which case all objects are shown. Or we have a logical exclusive OR, XOR, so in one image or the other image, but not in both, and in which case we highlight just the multiply and the divide symbols. Next thing we can use are filters, and these can be used for a number of different steps within image analysis, such as noise removal, edge detection, peak detection, and background correction. So one good example of this is a median filter, which can be used for reducing noise effects within your image, and it replaces your pixel X here with the median intensity of its surrounding pixels. So if you have a very large image with many pixels, it can take a little bit of time to compute this median filter. One other thing you can use is a background correction. So if your sample has been unevenly illuminated, you can correct for that. Ideally, it's better to not have a microscope with uneven illumination, but if you do, you can correct for that. And the reason we do this is that if you're trying to set up a threshold, but your baseline isn't flat, then it's very difficult to identify these peaks and these peaks within the same threshold. Next thing we'll use is find maxima, and again we use this as part of our cell segmentation activity. In this case, if we look at these nuclei, we can get Fiji to identify the peak intensity across this image, and in this case we use it to identify individual nuclei. And then if we use a watershed function, we can actually separate out these objects. And again, we'll use that watershed to produce segmented particles. We've got to find edges filter, so if this is something that you want to do, then again we can go into that nuclei image and basically draw a line around the outside of the structure. Now within Fiji, when it comes to quantitating, what we're going to use is the analyze measure function. So what I'm going to do over the next few slides, and this is the set measurements window, which gives you a lot of different options. We're going to, over the next couple of slides, just go through each of these options and explain what they are. So the first thing is to read out from Fiji. You need to go to Analyze Measure. That's Control M on a PC or Command M on a Mac. If you want to set what measurements that you want to read out, you need to go to Analyze, Set Measurements, and it will bring this up, and you select the relevant ones that you want. One of the most common readouts is area, and that's area of selection in whatever set units your image is. So if it's an uncalibrated image, it will be in pixels. If it's calibrated, it'll be in microns. One really important thing, and we'll do an activity on this, is to use this limit to threshold button. Otherwise, you will measure the area of the entire image, which might not be the most useful for you. Again, we've got an activity that uses this, but we can read out area fraction. So that gives you a percentage of the thresholded pixels within the image. You can use it for calculating your cell confluency or something like that. Next readouts we can read out our intensity. So we've got a number of different readouts here. If we select integrated density, we'll get two values. The raw integrated density is the sum of the intensity units in your selection. The integrated density is the mean gray values multiplied by the area. Your mean gray value is the average of the intensity units within your selection, which is basically your raw integrated density divided by the number of pixels within your area. You get a readout on the minimum and the maximum gray values within your selection. You'll also get a readout on the modal gray value. So that's the most commonly occurring gray value. So the top of your peak of your intensity graph. A median, which is the midpoint of the intensity distribution, and also a standard deviation as well. We can measure shape descriptors, so things like circularity, where perfect circle is 1. There's an equation for that there if you want to know how it's calculated. You can look at an aspect ratio, so if your particles are fitted with an ellipse, you can read out major and minor axis values. So here we'd have a major axis running this way and a minor axis running this way. We can read out roundness, which is your inverse aspect ratio. We can also look at solidity, so that's your area over your convex area. I like to think of this as if you take a rubber band and wrap it around your object, what would the difference be between the actual area of the object and what the area covered by your rubber band? So obviously, if you wrapped a rubber band around your circle, it would be the same area as the circle. If you wrap it around this star, the convex area is going to be much larger than the actual area of the star itself. We can measure out locations. So, for example, your centroid, which is the center point of your selection, or the center of mass, which is weighted for the brightness. So here we can see this object's brighter in the top right here, so the center's mass is skewed off to that region. We can look at the perimeter, so the length around the outside of your boundary, or what's known as the ferret's diameter, so the longest distance between 2 points on the boundary of your object. We also have bounding box, so the smallest rectangle which will enclose your selection, and again you'll get a readout of the sizes of the different sides of this box. We can fit an ellipsoid around your object, and again you'll get measurements out on the size of the ellipsoid, and we can also read out the stack position. We can measure intensity distributions, so there's a measure called skewness, which looks at the symmetry in X and Y, so is it symmetrically distributed or more asymmetric to the left or to the right? Or you can look at kurtosis, which is a flatness value in X and Y, so does it have a Gaussian distribution or is it flatter or more peaked than that? One of the other tools we'll use in the workshop today is Analyze Particles. And this allows you to not just take a single readout, but actually break up your images into smaller sections. So when we do the cell segmentation, we'll use Analyze Particles to do a per cell count and quantify per cell within the image. So the nice thing with analyzed particles is it allows us to do a little bit of filtering of the data. So we can filter based on size. And again, it's whatever your image is calibrated in, pixels or microns. We can filter based on circularity of the objects that you've identified. We can exclude anything that touches the edges, which can be very important. You don't want to quantify things that you can't see all of the object. And we can also get it to include holes. So if there's holes within your cells when you're setting up the segmentation, it will fill that in for you. Once it's done that filtering, you can get it to show a new image. So you have options for nothing, outlines, bare outlines, ellipses. We'll go through these in the next couple of slides. Okay, so this is the some of those options. So here we're excluding on edges, so you can see anything that's touching the edge of the image is excluded from the analysis. This is really important if one of your readouts is area, because obviously we're not capturing all of this object. Here we've got include holes, so you can see we've identified objects that have holes in them. By selecting include holes, they get filled in. And in this case, we're filtering based on size of objects and also their circularity. So if we're filtering 0 to 50 pixels area and circularity of 0.5 and above, then we get these very small circular objects. In this case, we're not filtering based on size, but we are filtering based on circularity, so anything below 0.5, which gives us these elongated or more globular structures. Again, we can narrow this down further. So 0.3 to 0.5 gives you the globular but not the elongated structures, and vice versa. And here, if we filter based on size, so 50 pixels squared up to infinity, and 0.5 circularity and above, gets us these larger circular structures. Okay, so you can use this to exclude things out of your analysis that you don't want to analyze. In terms of your show options, we have a number of different things. So this is after you've done that filtering step, it can produce a new image. You can produce an image that has outlines, so outlines around your objects with each one with a number. We have one called bare outlines. One's called masks that we can go on and use in the analysis as a binary mask. We have a representation showing you ellipses. We have count masks with different colors for each of the objects. Here we've got overlay outline, so it overlays on top of the image an outline with a number. And again, we've got overlay masks. And again, in our activities, we'll be using this masks option.